Welcome to Anything Maths. This video deals with displacement time and velocity time graphs. It's one of the series of videos that is going to look at motion under constant acceleration. Like the video and subscribe to the channel. We're going to look at velocity, acceleration, and speed to begin with. Velocity is the rate of change of displacement with respect to time. So that gives us a very definition that is looking at a small interval of time. But as far as this topic is concerned, we want to look at something that is more practical. So we're going to define what an average velocity is. So average velocity is given by displacement. And remember, this displacement is displacement with respect to the time, the starting point. But I'm just going to write displacement over time taken. Okay. So that is the average velocity. Average speed is total distance covered all divided by the time taken. So straight away we can see that the velocity is a vector quantity and the speed is a scalar quantity because it's defined in terms of displacement, and this speed is defined in terms of total distance. What about acceleration? Acceleration is simply acceleration is change in velocity over time taken. So that is what acceleration is. Please don't really read too much into it if you are also reading physics A levels, because with physics they can be a bit rigid to the definitions. This is maths. Let's look at displacement time graphs and see what we can learn in some of the characteristics of these graphs. We're going to look at three types of displacement graphs. So the first one we're going to look at is this. This is the first one. We want to label, so the horizontal will be time of seconds and the vertical axis will be x meters, and let's put 0 here. Okay, nice and easy. Okay, now imagine you move distance a meters, but you decided to rest for t1 seconds. So this is where the t1 seconds ends. So you are resting. Probably you've seen a friend and you are talking to the friend. This is how the graph is going to look like. Have you seen? So it means we are at the same distance, but time is moving. Okay. So when you see this sort of displacement time graph, it means the object or the vehicle or whatever you are considering is not moving. The second graph, let's label the second graph is t of x, that's seconds, and x of m meters, and let's put 0 here. Now imagine you are moving. This is a straight line. I can draw the straight line well, but let's make the assumption it's a straight line. Now what do you see? You can see that the change or the rate of increase of the displacement is constant throughout, and it's also constant over time. And when you look at it carefully, you begin to see that the gradient over here would represent velocity. But because it's increasing at a constant rate of change of displacement, it means it's going to be a constant velocity. So let's try and find the gradient of this line. You know that the gradient of a straight line at any point is the same. Let's try to cut here to be T2 and this to be T1, isn't it? And we can say this place will be X1, and we're going to get S2 here. The gradient is defined as, from your previous knowledge, it's change in the vertical, isn't it? Change in the vertical here over change in the horizontal. In this case, it's going to be x2 minus x1 divided by t2 minus t1. And this is equal to velocity. And because it's constant, it means whatever object or particle under consideration is moving with a constant velocity. This is so important. The third graph, let's label them the axis as always, because it's so important to do that. Do not forget to put your 0 so there is no where you're coming from. Now, imagine you have something like that. We can see that the increment within the displacement is not constant. Okay, it varies. So when it varies, the gradient at different points, the gradient at point, say, point A here is different from the gradient at point B here, and it's different from these at point C. And because the gradient is varying, it means the particle or whatever we are considering is moving with what? Different velocities. So this is not a constant velocity. So far, we look at 3 different graphs. The first one deals with when the particle or the object is not moving at all. The middle one, it says us that the object is moving with a constant velocity. And the last, the velocity is changing all the time. Let's have a look at the velocity time graph, because most of the questions are based on velocity time graph because they have many applications. So first of all, with the velocity time graph, we have to label them. So this one will be t of x and v of m per second. We have 0 here. Now imagine you are resting. The particle or the car is at rest for time t1. So up to this point, t1. How are you going to represent that on the graph? It means it's going to be here, and that will be that. It's not moving at rest, but time is moving. So that's the first diagram. When something is at rest, that is how you represent it on a velocity time graph. The second graph, we want to label it as always t of x, and we have v meters per second. Gonna have 0 here. Let's imagine the particle has a velocity va, but the velocity is not increasing for another t1 seconds. So we just draw a line parallel to that, to t1. What do you see? It means this is a representation of a particle moving with a constant velocity. Okay. This is a representation of a particle moving with a constant velocity. Now, when you find the gradient of this line, what kind of value are you going to get? It's going to be 0. So it tells us that if a particle or anything that is moving the constant velocity, then the acceleration is going to be 0, because as we looked previously, acceleration is changing velocity over time. And here the velocity is not changing, but time is changing from 0 to t1. So 0 over t1 will be 0. Okay, so this is really, really important. The next one, the third graph we want to look at, it's going to be different. So let's label that one as well. We have v m per second, and we have t of x, and we have 0 here. So this is moving from that to that. We can see that the velocity is changing, and the change is constant, isn't it? But it's also over time. So change of velocity over time is what defines acceleration. It means when we find a gradient of a velocity time graph, that will represent acceleration. It's so important. I cannot stress this enough. Okay, so let's look at how it works. Let's cut some few points as we did with previous one. Let's try and cut Maybe this is T2 and this will be T1. That will give you an equivalent of V1, and here we're going to get V2, isn't it? The gradient with respect to graph 3 will be change in V here will be change in V with the V minus 2, V minus 1 all over T minus 2, T minus 1. And this is the definition of acceleration, isn't it? Acceleration. So graph 3 is showing a constant acceleration. Graph 2 is showing a constant velocity. And graph 1 is showing, can you tell me? No movement at all for T1 seconds. I want you to think about a particle that is moving with changing acceleration, how it can be represented on the velocity time graph. As I said a short while ago, there are few things that are quite practical when it comes to the velocity time graph. So we're going to look at those few things because most of the questions are based on that. First of all, we can calculate the distance traveled using the velocity time graph. So let's see how this can be done. Now let's look at this graph. The one with the constant velocity. How can we calculate the distance traveled? The distance traveled, maybe let's put some broken line here. The distance traveled actually is represented by the area under the curve or under the graph. Now it resembles rectangle, isn't it? So the area will be VA, which is the value, VA times the length, which is T1. So this basically is VA T1. And this is also the total distance covered. And it's quite clear that from here, once you have the total distance covered, you can also find the average speed because you can divide it by T1 and get the average speed. Let's look at this diagram as well. The one with the constant acceleration. So that one also ends over here, which is T2. So we have T1. It's more of a triangle, isn't it? So let's say this is V1 as well. So the area under the graph is half base, because it's a triangle, times T1 times height, which is V1. So eventually become half V1 T1. which also give you the total distance. Okay, give you the total distance. And remember, once you know the total distance, you should be able to calculate the average speed by dividing it by t1. As I already told you, the velocity time graph is so important. This brings an end to this interesting video. Like the video, please, and also subscribe to the channel so that when I upload a new video, you're going to be notified.